Kevin Brosan, Matt DeLodge, John Hattas, Nate Lang, Ed Libano, Sam Roethlisberger, and Alec Tower, and our advisors are Dr. Vogelweed and Dr. Medeiros. In this presentation, we're going to discuss sort of an overview of the project requirements. I'm going to give you guys a glimpse of our budget throughout the project and some of the target specifications we had to design to. We're also going to talk about the finalized design of the robot and our testing plan moving forward. So to start us off, I'm going to give you a rundown of our overall project goals.
Oops, I think his system restarted or something.
Are we doing Skype or is it Teams?
We are on Teams, but
he's not in the meeting right now.
Yeah,
so he's back.
he's back.
I have no idea what happened. That's a little awkward. I'm sorry about that.
That's okay, Mr. Fan, don't worry.
Go back here. All right, let's go back to presentation. You guys see everything all right?
I can see.
Okay. So I'm just gonna sort of restart on this slide. So to start us off, I'm gonna give you a rundown of our overall project goals. This project revolves around the NASA Robotic Mining Competition, otherwise known as the Lunabotics competition. And the primary goal of the competition is to design and construct a robot capable of autonomously mining, collecting, and depositing simulated lunar ice crystals from underneath a bed of lunar soil simulant. This mining robot is meant to compete at the Kennedy Space Center in early May against 49 other university teams. Alongside the competition aspect of this project, NASA requires that teams not only focus on bettering their own skills, but bettering their community as well. Although this presentation will focus on the technical aspects of our project, I felt it was sort of important to mention this fact. The outreach efforts required by NASA included helping K-12 students and motivating them towards careers in STEM. To do that, our team volunteered twice a week at Prince of Peace School. It's in the Milwaukee area, and we helped out their LEGO robotics team. Moving on, I'm going to give you sort of a brief rundown of the project budget. The budget's changed dramatically throughout the course of the project as we seek sponsors from various sources in every avenue we possibly could. This table shows the estimated project expenses at a certain date broken down by where these costs were allocated. The last two rows are going to be what I'm mainly talking about today. So the last two rows are the total cost at that given point in time and the total funding we had acquired. So in the beginning, you see we had a pretty high estimated cost, but at the same time, we only had about $8,000 in secured funding, so we had to work on that aspect a lot. So as the project progressed, we were able to reduce our costs significantly while also being able to receive more funding. And in the end, we came in under budget and successful. Now I'm going to hand it over to Alec, and he's going to walk you guys through some of our target specifications.
All right, so since we did not have a formal customer for this competition, our target specifications and design requirements were more set by the competition. And then these were also set to help ourselves do the best that we possibly could within the competition and try to win the competition. So obviously one of the biggest requirements is making sure that we're able to move throughout the arena without getting stuck, and then being able to dig to a depth of at least 35 centimeters, because within the testing arena, there is 35 centimeters of the lunar soil simulant before you get to the icy regolith, which is what we're aiming to collect. We needed to be able to collect at least 1 kilogram of icy regolith, so we set a goal trying to collect at least 1.5 kilograms. And then on top of that, we needed to be able to lift the material up to a height of 35 centimeters, because that is the height of the collection bin where we needed to deposit all of our icy regolith. And then finally, our robot had to be within the size specifications. So in previous years, the robots were allowed to be much bigger, but for this new competition, to align with NASA's goals of heading back to the moon, they set a new size requirement of 0.5 meters by 1 meter by 0.5 meters tall. And then next we will talk about our target score on the next slide. So based off of what we have seen in previous competitions and how teams have scored in previous years, we went through and decided what would be best for us and the goals that we wanted to aim for ourselves. NASA scores teams based off of things that they do well, like digging more gravel and implementing some level of autonomy, but then they can also take away points for things that would negatively affect a space mission, such as increasing the mass of the robot, increasing the amount of energy, and increasing the amount of bandwidth used for data transfer. So combining all those factors, we generated a target score of 1,179. And based off of the 2018 competition, we would have won this competition by at least 30 points were we able to meet all of our target specifications and meet our target score. And then I will hand it off.
Thank you, Alec. So now we'll get into the final design of the robot. The final design of the robot is shown there. It uses 6 motors, 1 actuator, 3 gearboxes or chain and sprocket mechanisms, and a LiDAR safety sensor. The dimensions of the robot, it falls in at about 0.49 meters wide by 0.98 meters long by 0.49 meters tall and weighs approximately 40 kilograms. So we fall under all of our target specifications in that regard. Next slide, please. For the mechanical design of the robot, the design was divided into 3 subsystems: locomotion, digging, and dumping. This modular approach allows each subsystem to be designed, tested, built, and repaired independently. Next slide, please.
All right. So the first major component of our the mechanical design was the locomotion system. We decided to use a tread design using 2 motors, 1 for each tread, that could be controlled independently. The reasoning for choosing this design was based more off of what we had available and off of prior competitions. We found that treads were roughly 50% more reliable than wheel designs, allowing us to meet our target specification of being able to traverse without getting stuck. These treads are also able to make approximate 0-point turns, which makes it much easier for controlling and being able to map where we are within the arena from an autonomy standpoint. These treads are also able to traverse obstacles much more reliably. That is kind of why tanks use tread designs, because within the arena there are craters and boulders that we must traverse over. They can get up to 25 centimeters deep and up to 25 centimeters tall. Did Mustafa leave again? Okay.
Yeah, looks like it.
No.
It's okay. We'll just wait.
Yeah. Okay.
I have no idea what's happening with my computer.
That's all right. Okay, so because of the size of these obstacles that we must traverse, treads are a lot more practical because they distribute the weight evenly, so we can begin to roll over some of the craters within the arena without getting stuck inside of them, and also try to roll over the boulders without bottoming out. And I will hand it off for the next piece of our mechanical design.
All right, next we're going to look at the digging mechanism. And after narrowing down from 4 initial designs, the team came up with this design here, which is called the zipper drive. This design uses a belt with 17 scoops that is rotated by a single brushless DC motor. The zipper is propelled into the ground using a rack and pinion style gear and shaft. With a simple gear train, this design allows for the actuation into the ground to be done by a single brushless DC motor, and it also greatly reduces the amount of framing components needed, which reduces the overall footprint of the design and reduces the weight as well. All in all, the zipper can reach a depth of over 37 centimeters. The pitch of the zipper drive is controlled by a stepper motor connected to a right angle gearbox by a chain and sprocket. The zipper is long enough and has enough clearance to compensate for slight variations due to inaccuracies in the stepper motor. Another thing worth noting is that the scoops are designed to be made of CNC aluminum. This allows for an increased rigidity and less likelihood of catastrophic failures that we saw in scoops that were made out of rapid prototyping material. Now Mustafa will talk about the dumping mechanism of the robot.
All right, so I'm not going to turn my camera on because that might have been what messed up my computer before. I'm not really sure, but so the dumping mechanism was designed around the shape of the zipper and the height requirements of the collection sieve in the competition arena. So this system has 2 degrees of freedom, which are controlled by a linear actuator right here and a motor. The linear actuator drives the dumping bucket up 2 parallel guide rails, and the motor rotates the bucket and its contents to release the collected material into the collection sieve. The actuator and the motor are both selected to handle the load capacity of the dumping bucket when it's completely filled with material. That way we could make sure it handles it even if it's half full, anything like that. And in order to reduce the bucket weight, though, and avoid a fully loaded bucket, because we don't want to carry around a full bucket of dirt, holes were punched into the bottom and a vibration input's going to be input with the motor. That way it acts like a sifter, like if you were sifting powdered sugar over some cookies or something. With this design, we're able to reliably reach our 50 centimeter height requirement for the collection sieve because of these arms especially. So when it gets up here, it pivots about the bar over here. That allows it to fully rotate and fully achieve the height we need. That basically covers the mechanical design. I'm going to hand it off over to Sam, and he's going to just walk you guys through the electrical design.
Okay, so for the electrical design, I'm going to kind of go over just kind of what the networks were, and then specifically why we used some of the hardware components that we did. So the onboard computer that we used for the robot was an Udo, and this is a quad-core processor made by Intel. And then for Udo 2, shown right here, we also attached a Wi-Fi Intel dual band antenna, which allowed us to communicate via Wi-Fi to a wireless access point so that from the command room, we could communicate with the robot. So Network 1 had one Udo that was fed into Network 2 Udo via a male-to-male Ethernet. Network 1 was primarily used for the LiDAR or the safety sensor, and then Network 2 was used for the controllers and all the motors. So for the controllers, we used 3 O-Drive controllers and 1 RoboClaw controller. We used O-Drive controllers because they controlled brushless motors, which our 6 motors were. You can control 2 motors for each controller, and it also had a pretty easy USB interface, which allowed us to use also ROS node, which was very important because that's what we wanted to use to program. And then it also had velocity and position controls for our motors in case we needed those as well. And for our RoboClaw controller right here, we had our actuator controlled off of that, and we needed to operate that at a lower voltage and current than the other controllers, which was fine because the actuator, that's what the actuator needed. So we had 2 different networks. We split these into 2. Initially, they weren't 2, but we decided to plan for this because the LiDAR needed a constant supply voltage of about 24 volts. And we didn't want it being interfered with by any of the other components. So we kind of just decided to just have 2 separate networks on different power supplies. And also the Udo 2 was pretty congested with all the inputs from the controllers, and there was actually like no space left on the Udo 2 So we just opted into getting another computer basically that would feed into the Odoo 2 to transmit and receive data from the command room. As for the power limitations, it seems like there's a lot of batteries here, and but we didn't really take into account the power limitations too much. We would lose 1 mining point for each watt hour consumed. But as far as like the standards, there wasn't like a set standard for that, so it wasn't our biggest concern. Next, Ed is going to talk about some other components for the electrical team.
So the remaining electrical components were primarily for safety reasons. So among our specifications were to meet certain safety verifications and make sure that we had a way to keep track of how much power we were using, be able to stop the robot in the event of an emergency, and then just general sensors so we could have more idea of what exactly was going on with the robot in different parts. So our first part was our power display. That was again required by NASA just to make sure that we could keep track of how much energy we were using, keep track of like the voltage across from our power source going to each of our different components, and keep track of the amount of current that's flowing through that as well. This was mostly used on NASA's part for scoring purposes, but we could also use it to keep track of, making sure that we're within safe specifications. The emergency stop button was again another safety goal. The point of the emergency stop button is to be a mechanical switch that would be able to shut off power to any of our motors and their controllers. In the event that anything goes wrong, anything is dangerous, the robot is posing some kind of harm or potential harm to something. So that was the primary goal for the emergency stop button. That also was another explicit specification from NASA for safety purposes. And then finally, we had a few different sensors other than the LiDAR. They consisted of accelerometers and a couple different points on the robot just to make sure that we could keep track of, have a better idea of where the robot was, how it was moving, and that would mostly be feeding back to the control room. All of these parts were chosen based on their abilities to handle our voltage limits, our current limits, and we usually made sure that they were far above what we were actually using just to make sure that we would be able to handle the amount of power that was going through them. And next, Nate is going to take you over the basic architecture of the software that we were using.
Thank you, Ed. So for the computer architecture, we chose to go with a model view controller structure because it is a common architecture and provides good maintainability. So we have put a little twist on this where our layers are actually definition, services, and implementation. This is because ROS has a lot of features we want, such as their services part, although it is still a model-based system, which are called nodes in ROS terms. The definition layer is making the robot structure and breaking it into subsystems. Then the goal of the services layer is to limit the repeated code, such as calculation functions. Then lastly, the implementation layer is essentially the ROS functionality. On the right-hand side, you can see a picture where we show our structure between the services, implementation, and definition layers. And so the goal is each component of the robot, such as a motor or an actuator, is defined in the definitions. Then the services layer serves as an interface between the definitions and the implementation layers. I will now pass it off to John for a more of a ROS explanation. Thank you.
Thank you, Nate. So in order to implement the architecture Nate just discussed, we use the robot operating system, or ROS, and all the robot code is written in Python using ROS's robot software framework. ROS helps us organize our code into separate nodes, where each node is specialized in one component of the system, namely digging, dumping, or locomotion, and these are the three subsystems the mechanicals discussed. All nodes are controlled by one single ROS master node, and there's also an additional ROS node for communication and controlling the robot from our laptop, and you can see this in the diagram on the slide. And one of the big reasons for using ROS is it has a really active community with packages created for most common peripherals, including our O-drive motors and the LiDAR. And these ready-to-use packages allow us to focus on the architecture, air handling, and the interaction between the subsystems. So now I'm going to pass it off to Kevin to talk more about the LiDAR.
Thanks, John. I apologize my camera's not working on Teams today, but one of NASA's main focuses for the competition this year was autonomy. In order to achieve this goal, we decided to go with a LiDAR rather than a camera. We created a design matrix with both the strengths and weaknesses of the LiDAR and camera. And due to the LiDAR's lack of complexity and lower development time, we decided to go with the LiDAR. Specifically, we chose to use a SICK LiDAR based on Dr. Medeiros' recommendation and because he was willing to loan us one, but it has built-in ROS libraries which significantly reduce development time. We would use a 2D LiDAR, which creates a map of the arena, and we can use this to localize the robot within the map. Once the robot is localized in the arena, it will be able to see the obstacles and goals that we set for it, and it can begin to transverse the arena autonomously. As it transverses this arena, it will be able to update where it is and where the obstacles and goals are in relation to it, and it can go and do that until it reaches its destination, or we manually override it if something goes wrong. At minimum, this will allow us to perform partial autonomy, which was our target autonomy goal. Next, Mustafa will show a simulation of our robot.
All right, so this is what our robot's going to look like when it's doing a mining attempt. This is after it gets to the location where it's going to dig. The zipper will rotate about this gearbox to our angle of attack of about 70 degrees. Once it reaches that angle, these wheels are going to start turning, so the belt's going to start rotating and the scoops are going to start rotating around it. That's too much to do in our CAD model, but you know, it's good to visualize this way at least. Then it digs down to our maximum depth of 37 centimeters. All the while, these scoops are rotating and collecting and dumping the collected material into the dumping bucket over here. So after it's done, the zipper will come back up. Then you'll see the wheels start to turn as it goes back to the dumping bin. So now you'll see the wheels turning. And once it gets to the dumping bin, it reverses. So this is all, I'm calling this on the back of the robot. It reverses and lines the dumping bucket with the collection seat. The dumping bucket then rides along these guide rails propelled by the actuator. And once it gets to the top of these guide rails, it rotates. So you see here, that's how we plan on dumping it reliably and effectively. And look, it goes really high. 50 centimeters is about this height, so it goes well over that height requirement. Now I'm going to hand it back over to Kevin. I don't think we need to see this thing closing itself back up. So Kevin's going to talk you guys through the testing procedure.
So in order to verify that our robot functions as designed, we need to test our robot. We came up with a test plan that involves bench testing on individual subsystems as well as a full system test. This was possible due to our modular design, as noted before. We plan to create a small simulated environment for the robot behind eHall. We were going to use sand and gravel as a simulant for the lunar surface because of its cost effectiveness, durability, safety, and disposability. Our testing plan had both minimum and target requirements. The minimum requirements aligned with NASA's minimum requirements. Mostly, is it safe and does it function? While our target requirements aligned with what our robot needed to do to reach our target score in the competition. Next slide, please.
All right, so I'm going to talk you guys through some of the basically the major obstacle we encountered through this project. Obviously, it has to do with the pandemic. So before spring break, we had the robot about 90% completed. Electrical and computers were still working to get everything fully operational. Obviously, we couldn't really do anything after we couldn't go back to school because our project's really hands-on. It's building a robot. So in order to ensure success, we decided to shift our focus from success in this year's competition to success in next year's team. We shifted our focus to providing a really solid foundation for next year's team and giving them every opportunity to succeed they could get. To do that, because the competition was canceled due to the pandemic, we were able to reallocate our funds there and purchase 2 LiDAR systems. That way we don't have to borrow any when we have 2 of our own. One is obviously to localize the robot parallel to the plane of the arena, and the other one is to be able to see the different terrain and what the robot's actually about to encounter, and be able to adjust accordingly from there. So that ends our presentation. I'd like to thank you all personally for your support throughout this entire school year. We really appreciate the efforts you guys put into supporting us and all the help you guys have given us and all the advice and guidance and all that. We'd also like to thank our sponsors seen here on the screen. Without them, this project wouldn't be possible. And now I'm going to open up the floor for questions.